Hello friends, this is Vishnu Maurya. In this video, we will quickly revise the subject hydraulic machine. In this subject, we will start with hydroelectric plants. What are the hydroelectric plants? In this, the sequence in which water flows starts from a reservoir onto some river or canal. From the reservoir through dam, it will reaches to through the penstock to this turbine. Okay, into this turbine arrangement, and we have a surge chamber. Now through this turbine, the rotation of the turbine, the generation of the power is being done in motor generator, and the water that will be coming out of this through draft tube, and it will reach to the tailwater pond. So we will see that through the dam or through the sluice gate, we have a canal to forebay. Here the water will accumulate through the penstock. It will reach to through the powerhouse. It will reach again in the tail race level. Okay, so these are the intake structure and these are the waste water. Now we will see that what are the forebays. Forebays are the enlarged section of the canal spread out to accommodate the required width of the intake. Okay, so these are the enlarged section of the canal. This is the canal and this is the enlarged section of the canal that is spread out to accommodate the required width of the intake structure. Okay, and what are the surge tanks? Surge tank are present here. Surge tank are the opening made in the long pipeline to receive the rejected flow when the pipeline is suddenly closed. Okay, so this is the penstock in which water is flowing. If this gate is suddenly closed, then there will be a backwater pressure, that will be water hammer pressure. Water hammer pressure can be removed using this surge chamber, so that effect can be reduced using surge chamber, and there will not be a case of the failure of this pipeline. Now penstock or the pressure pipe carrying water. This hydraulic turbine, this convert hydraulic energy into mechanical energy. Draft tube, this is the conduit which connects the outlet of a reaction turbine, that is the reaction turbine runner, to the tail race. And what is the tail race? Tail race are the waterway to conduct water discharged from the turbine. Okay, now we will see the heads. What are the gross head and net head? Gross head is the difference between head race and tail race, and net head is obtained by subtracting all the losses from the gross head. Okay, so you can see this is the head race and this is the tail race. So from these two values we obtain the difference of these will give us the gross head, and if we reduce the losses from it, then we will get to know the net head. Now there are a few terms which are very important to memorize: water power potential, load factor, utilization factor, firm power, etc. So water power potential is the power generated, that is the water power given by gamma Q into H in kilowatt. Gamma W is 9.81 kilonewton per m cube. Q is the discharge flowing and H is the net head. Now load factor is the average load over a certain period upon peak load during that period. Okay, and utilization factor is water actually utilized for power production divided by the water available in the river. These two terms are very important for objective point of view. And what is the firm power? Firm power are the net amount of the power which is continuously available from a plant without any break on firm basis. Okay, so this is the maximum, that is a net amount, the power, that is the minimum power that is always available. Okay, or we can say the maximum amount of power that is always available through the plant without any break on the firm basis. Now what are the secondary power? Secondary power are the excess power available during off-peak hours. Okay, so this is the excess power over the firm power. Now we will start with the turbine. Now turbine are of two types, either impulse turbine or reaction turbine. So first of all we will see the impulse turbine. An impulse turbine is a turbine that is driven by high velocity jets of water or stream from a nozzle directed onto the vanes or bucket attached to a wheel. The resulting impulse spins the turbine and removes kinetic energy from the fluid flow. So in this, an open arrangement is there, that is a kind of the Pelton turbine, in which the turbine is driven by the high velocity jets. The jet will hit the vanes or the bucket attached to the wheel. Now the resulting impulse spins the turbine. Turbine will spin because of this, and the kinetic energy is used from the fluid to convert it into the mechanical energy. Now H, that is H obtained, will be P1 upon gamma plus V1 square upon 2G plus Z1 minus Z2 in case of the Pelton turbine. Now we will see the flow sequence in the Pelton turbine. From the reservoir, the water comes out and it reaches to the penstock end. Before that, there will be some head loss in the penstock, that is represented by HF. Now the reservoir, at the level of reservoir, we are having the gross power from the reservoir. Now when it reaches the penstock end, it will be having net power from the reservoir, that is H. And now power supply to the wheel, that is wheel horsepower. Okay, so this will reach at the nozzle end, and from the penstock to the nozzle end, penstock end to the nozzle end, we will be having the head loss in the nozzle. Now after the nozzle end, it will reach the turbine wheel, the water will reach the turbine wheel, and at the turbine wheel, we are having power developed by the wheel. So before reaching from nozzle head to turbine wheel, we are having hydraulic loss and leakage losses. Hydraulic losses are because of bucket friction, eddy formation, or energy contained by the water not hitting the bucket. And at the turbine wheel, after the turbine wheel, we are having some mechanical losses before reaching the shaft. Mechanical losses due to the bearing friction, and the power developed from the shaft is available at the shaft level. Now after the shaft, it will reach the generator, where the power developed by generator, and it is used for the distribution purpose. Now before shaft to generator, we are having some generator losses also. Now we will see the case of the reaction turbine. Reaction turbine is a type of turbine that develops torque by reacting to the pressure or weight of a fluid. In this, we are not having an open system, so it will be a closed system. And the examples are Kaplan, Francis, propeller, Fournier turbines. And H will be P1 upon gamma plus V1 square upon 2G plus Z1 minus Z2 plus V2 square upon 2G. So in this, if we see the flow sequence, it will be similar to the previous one. There are a few differences only. From the reservoir to the entrance of spiral casing. Okay, in the previous one, it was reaching to the nozzle end. Here it will be reaching to the spiral casing, and there will be the head loss in the penstock. Now the net power from the reservoir after reaching to the turbine runner, that is the power developed by the runner, we are having losses of hydraulic loss and leakage loss. Okay, so in the spiral casing to the turbine runner, we are having these two losses. Hydraulic losses are due to blade friction, eddy formation, and friction in the draft tube, and there are leakage losses also. Okay, leakage due to the leakage of the water. Now power developed by runner is produced at the turbine runner. Now turbine runner to the shaft, we are having some mechanical losses due to bearing friction, and the similar case will be after this to the generator, and some generator losses are there. Now we have to note one thing here, that impulse turbine requires high head. Okay, that is head more than 250 meter, and low quantity, that is the low discharge. But the reaction turbine require lower head and high rate of flow. This is very important, usually asked in objective type of questions. Now we will see the efficiencies. Efficiencies like hydraulic efficiency, volumetric efficiency, mechanical, and overall efficiency. Hydraulic efficiency is the power developed by the runner upon net power supplied at the turbine entrance, that is gamma QH. Okay, and volumetric efficiency is the discharge actually striking the runner upon quantity of the water supplied to the turbine. Now before this, we are having some leakage losses, that is delta Q. So Q upon Q plus delta Q, that is the volumetric efficiency. Okay, and mechanical efficiency is shaft power upon runner power. Now overall efficiency will be the multiplication of these three, that is hydraulic into volumetric into mechanical. Now what is overall efficiency? That is power available to the turbine shaft. Now finally at the shaft level, we are getting the power. Okay, and the power available to the turbine shaft upon the net power supplied at the turbine entrance. So at the turbine entrance, that is, we can see here net power supplied at turbine entrance to the shaft power, we are having overall efficiency. Okay, that is shaft power upon gamma Q plus delta Q into H. Now specific speed is a term. This is very important term. Specific speed is the speed of geometrically similar turbine which would produce unit power under unit head. So NS can be represented N root P upon S raised to the 5 by 4 RPM. Okay, so it is the specific speed, that is the speed when we are supplying 1 unit of power and providing 1 unit of head. Okay, so this RPM value for the different turbines are given here. For Pelton wheel, we are having NS from 10 to 35 because these require high head and low discharge. Now Francis turbine having 60 to 300 and Kaplan turbine 300 to 1000. So we can see here that Kaplan turbine are the best in terms of the specific speed, and specific speed is the which defines the efficiency, that is how good a turbine is. Now we will see Pelton wheel turbine. Pelton wheel turbine, we can see the water coming from here. From the penstock, it will reach as the nozzle level where we are having a spear. From this arrangement, we can increase or decrease the quantity of discharge that will be coming out. It will hit the hemispherical shaped bucket here. The runner will start rotating because of these blades. This is the D1. D1 is the diameter of this arrangement, and the water which will come out will reach the tail race level and it will be taken out through this arrangement. Now velocity of jet here will be the velocity coming out of this, that is velocity at the vena contracta. When the fluid will come out of this, so there will be a portion where we are having the vena contracta, that is where the area will be minimum. So that velocity will be the velocity at the jet, velocity of jet, v1 equal to kv1 root 2 gh. Okay, h is the total head that is possessed by this penstock. Now q equal to pi by 4 d square into this v1, that is velocity of jet, and d1 is the dia of the water jet at the vena contracta, and v1 is the velocity at vena contracta. Okay, now u1 is the pi d1 into n upon 60. This is the velocity through which this arrangement of the Pelton wheel turbine will rotate. Okay, now this is also called circumferential velocity, and there is a term jet ratio of Pelton turbine, that is m equal to mean diameter of the turbine upon least diameter of the jet, that is capital D1 upon small d1, and this m value lies from 11 to 14. So mean diameter of the turbine is this is the turbine dia, and least diameter of the jet, that is diameter of jet. This is the diameter of the jet, and this is the diameter of the turbine. We will see now the reaction turbine. Reaction turbine, we can see here that this is through the penstock, the water will enter into this arrangement of the stay vane, then runner vane, then the guide vane, and then to the runner blade. So it will rotate, and this will be connected to the shaft, and the electricity will be generated from it. This is the spiral casing. Spiral casing is the closed passage of the gradually reducing cross section, that is the cross section will reduce in this closed passage of the spiral casing, and enclosing the runner. It distributes the flow over the periphery of the runner such that the entrance velocity is same all around it. Okay, now stay ring. Okay, this is stay vane or stay ring. Outside ring of the guide vane, it is the fixed vane, and it acts as a column helping to support the weight of the non-rotating part of the turbine. This is of the airfoil shaped. Okay, and guide vanes are inside this. These are of cast iron, and usually its number are 8 to 24, and since it is pivoted, so it can turn also. This is also of airfoil shape, so that heating of the water does not cause energy loss. This is the runner vane. Runner vane is also made up of cast iron or cast steel. The rotating element of the turbine is the runner vane only, and through which the shaft is connected. Discharge here will be pi d1 b1 into vf1, where vf is the velocity of the flow of the water through the penstock, and d1 and b1 is the dia as well as the width of this turbine arrangement. We can see here that d2 is the inside dia and d1 is the outside dia about this guide vane. Okay, now u is the peripheral velocity. U is pi dn upon 60. We have seen it earlier in the Pelton turbine also. Now we will see the draft tube concept. Draft tube is after the water coming out from this arrangement, after this runner blade or vane, since it has rotated this shaft, so now the water will come out through this turbine through draft tube. Okay, so we are having draft tube. Why we are having draft tube? We can see here it connects outlet of the runner to the tail race. It is of steel pipe, and cross section gradually increases to avoid cavitation. So main function of the draft tube is to gradually increase its cross section so that cavitation cannot occur into this section. You can see here that through the spiral casing, it is water reaching through the guide vane to runner vane. This runner vane is rotated, so this shaft is also rotated, and the water will come out like this through the draft tube, and it will reach the tail race level. At the tail race level, we are having atmospheric pressure, so this pressure has to reach the atmospheric pressure. So the kinetic energy which is possessed by this water after coming off the runner, this kinetic energy is converted into the pressure energy. Okay, and this will reach the pressure energy equal to atmospheric pressure. Now function is similar. I have told it that converts kinetic energy of the rejected outlet into useful pressure energy. Now efficiency of the draft tube can be determined by actual conversion of kinetic head in the pressure head upon kinetic head at the inlet of the draft tube. Okay, so at the inlet of the draft tube, we can see here that kinetic head can be given by the V2, and at the V3 we are having actual kinetic head remaining. Okay, so we can write it as V2 square by 2g minus V3 square by 2g minus some head losses. Head losses are the losses that occur when water reaches from this point to this point, that is from this level, runner blade level, to the tail race level. Okay, so head loss is not being converted by draft tube, so this will not be accommodated into this arrangement of draft tube, okay, into the efficiency of the draft tube. Upon this kinetic head is V2 square upon 2g. Okay, now the type of the draft tube, there are 4 kind of draft tube which are employed into the arrangement of this turbine. It can be straight divergent tube, it can be Moody spreading tube or hydrocone, and simple elbow tube or elbow tube with the circular inlet and rectangular outlet section. Now straight divergent tube are of frustum shape, and these are employed at the low specific speed, that is at the specific speed value, low specific speed. In the case of some reaction turbines, maximum efficiency reaches 85%. The Moody spreading tube or hydrocone is bell mouth draft tube, okay, and these are having solid conical core in the central portion. We can see here this is conical core, okay, and the central portion reduces whirl action of the high speed eddy forming discharge, and efficiency is about 85%, and it is used for high speed reaction turbine. Now simple elbow tube, these are of minimum cost, efficiency is about 80%. You can see here the dia increases from starting level, from the turbine level to the tail race level. Now elbow tube with circular inlet and rectangular outlet section to turn water from vertical to horizontal direction. Now we are having Kaplan turbine and propeller turbine. The difference between them is the arrangement of these runner vanes. In the Kaplan turbine, these are adjustable runner vanes, and in the propeller turbine, these are the fixed blades. Now efficiency of the Kaplan turbine is more than propeller turbine, and the water in the Kaplan turbine after guide vanes turns through 90 degree into the axial direction and then passes through the runner. So in the previous arrangement, we were seeing that from the guide vane to the runner vanes, it was reaching into the same plane, okay, into like this. Okay, but in this arrangement, in the Kaplan turbine, we can see that this water will come downward into, it will change its direction to 90 degree, and it will come out at 90 degree to the direction in which it has entered the guide vane. Okay, so it will change its direction from that is 90 degree into the axial direction and then passes through the runner. Now runner has 4 to 6 vanes, while in Francis it is 16 to 24. Okay, so in this has 4 to 6 vanes, and reduction in the contact surface with water ensures low frictional losses in the Kaplan. Now part load efficiency of the Kaplan is large because it has adjustable vanes, and the discharge is given by pi by 4 dO square minus dB square into Vf. You can see here that dB is the boss or hub dia, and dO is the overall diameter of the runner vanes. So we can see here, and Vf is the velocity of the flow, so discharge can be given by pi by 4 dO square minus dB square into Vf, and Vf can be determined by psi into root 2gs, where psi value is from is about 0.7. Now we will see the cavitation in reaction turbine. Cavitation is the process which occurs if the pressure of the liquid becomes less than the vapor pressure. Cavitation is a process which can destroy a turbine. So here we can see the pressure at the P2 level, that is pressure outside this turbine, that is arrangement in the draft tube. It can be given by P2 upon gamma, that is P ATM upon gamma minus HS minus 1 minus K times V2 square minus V3 square upon 2G. Okay, we have seen it in the draft tube. So this P2 value, this pressure, if it becomes less than vapor pressure, so the cavitation will occur, and cavitation is a hazardous process, we know that, and the cavitation factor can be given by sigma equal to HA minus HV minus HS upon H, where HA is the average atmospheric pressure in meter of water, HV is the vapor pressure in meter of water, HS is suction pressure head in meter of water, and H is the working head of the turbine in meter. Vapor pressure actually is a function of the temperature of the flowing water and the absolute pressure due to location of the turbine above MSL. Now the suction pressure HS, this is the suction pressure. HS can be given by height of the runner outlet above tail race level. Now efficiency of the draft tube can be given by this cavitation factor only. There are some methods to avoid cavitation. The methods are installation of the turbine below tail race level, use of the macking, that is blades are highly polished, welding cavitation resistant metal pieces powder on the surface likely to be exposed to cavitation damage, and some metallurgical treatment like cold treatment, rolling, etc. to harden the surface. There are some unit quantities. We will see turbine parameters which are obtained when a particular turbine is operated under unit head. Okay, under unit head, what are the terms we obtain? We give it by the term unit quantity. So we can see the unit quantity is a unit speed, the speed at which the turbine is rotated, that is given by n value of the same turbine can be given as n1 upon root h1 equal to n2 upon root h2. If at the h1, that is at the h1 head, if we are having the turbine turbine running at n1 speed, then at the h2 we are having n2. that is the speed of the turbine at H2 head. Now unit discharge is Q1 upon root H1 equal to Q2 upon root H2 equal to Q3 upon root H3, and unit power is P1 upon H1 raised to power 3 by 2, P2 upon H2 raised by 3 by P3 upon H2 raised by 3 by 2. Now specific speed can be given by N root P upon H raised to power 5 by 4. We have already seen specific speed. Now model relationship between these two in the model and the prototype. This can be given by Nd upon root H of the model equal to Nd upon root H of the prototype. If discharge is given, then Q upon Nd cube of the model equal to Q upon Nd cube of the prototype, and in terms of the power, P upon N cube d raised to power 5 of model equal to P upon N cube d raised to power 5 of the prototype. After turbine, now we will shift to pumps. Pumps are the mechanical devices to increase the pressure energy of a liquid. So through this pressure energy, we can take out water from any reservoir or some unit of the water. Now positive displacement pump, these are reciprocating pump. In this the fluid is directed into a closed volume, and in the rotodynamic pump there is no closed volume. Instead, a rotating blade supply energy to the fluid. So positive displacement pump are of type of the hand pump, and rotodynamic pump are of the pumping set arrangement. Now reciprocating pump, in which we can see that there is suction arrangement. There will be a case in which the pressure will be below atmospheric pressure, and there can be possibility of the formation of the vacuum also. So we can see here that through this sump level, this water is taken out into this cylinder. When this is piston is being taken back using this crankshaft arrangement, we are having connecting rod. This is piston rod, this is cylinder, and this piston is being taken back by rotating it. Now we can see when it will go back, this valve is open, the fluid will flow inside it, and when we are taking out the water, this delivery valve will open and the water will be taken through the delivery pipe. Okay, so there are two cases, either single acting pump or double acting pump. So I have seen what I have told is the example of the single acting pump. In the case of the double acting pump, if in the case of the delivery, since this portion will be having no water in case of the delivery, so in this case, if this is filled by the water, then that will be the case of the double acting pump. Now these are defined according to the water being in contact with one side or both side of the piston. So we can see here that this is one side of the piston, this is second side of the piston. If water is being at the both side, then it will be case of the double acting pump. This is HS, that is from the sump level in the suction pipe. Okay, from the sump level to this level of the piston, and from the piston to this delivery pipe we are having HD, that is the head. Now discharge can be given by theoretical discharge through ALN upon 60, that is single acting, and 2 ALN upon 60 for double acting. N is the speed, L is the length of this section, that is cylindrical section, and A is the cross section area of the cylinder. Now what is slip? Slip is the theoretical, that is this theoretical discharge minus actual discharge. Okay, and percentage slip will be Q theoretical minus Q actual upon Q theoretical into 100. Now coefficient of discharge will be Q actual upon Q theoretical, that is generally CD value less than 1. But in case of the negative slip condition, CD value will be less than 1, and it occurs when the delivery pipe is short, suction pipe is long, and pump is running at the high speed. So this is the case of the negative slip condition. Now work done by this pump can be given by gamma into Q theoretical into HS plus HD. This is the total head. Okay, and gamma is the gamma W, and Q theoretical is the theoretical discharge that we have obtained here. Now we will see the case of the centrifugal pump. Centrifugal pump are having the dynamic pressure developed, which enables the lifting of the liquid from a lower to a higher level. Okay, so this pressure, through this pressure arrangement, we lift the water from lower level to higher level. This is the eye. Okay, this is the impeller. From the eye, we get this water from any unit from where we have to lift the water. Now through the impeller vanes, the direction is being defined for the water, and after this in the volute casing of increasing area, the water will flow out and in terms of discharge. Now thus pumps convert the mechanical energy to the hydraulic energy, and it works on the principle of the forced vortex flow. In this we are having the forced vortex flow. Now classification based on the working head: low lift centrifugal pump, medium lift, and high lift. Low lift is the case in which the head is less than 15 meter, medium lift in which it is 15 to 40 meter, and in case of the high lift we are having head more than 40 meter. So in case of the 15 to 40 meter medium lift centrifugal pump, we use the guide vanes. And for this high head, if we used to take out the water from very lower head to very high of more than 40 meter, then we have to use multi-stage pump. We are having more than one turbine in this case. Now classification of these pump based on type of impeller, either closed or semi-open or open. Closed is for clearer water, semi-open or non-clog pump for sewage water, and open is for the sandy water. A static head can be defined here using HS plus HD, that is suction head plus delivery head, and it is the difference between the water level in the sump and the top storage reservoir where the water is stored after pumping. And manometric head is the HS plus HD plus HFS plus HFD plus VD square upon 2G, where HFS, this friction loss, this is given by friction loss in the suction pipe, HFD is friction loss in the delivery pipe, and VD is the velocity of the discharge. Now if it is the total head, manometric head is the total head that must be produced by a pump to satisfy the external requirement. So this manometric head, net head imparted by the pump, can be given by VW to U2 upon G, that is head imparted by the pump minus loss in the pump. Loss will be in the casing as well as in the impeller. Now we will focus on some efficiencies in the pump. Efficiency can be manometric, volumetric, or mechanical, and the overall will be the multiplication of all these three. These are similar to the case of the turbine. Manometric efficiency given by manometric head upon VW to U2 upon Z, power imparted by the impeller equal to shaft power minus mechanical losses. So this is power imparted by the impeller. We determine it using shaft power minus the losses that occurs due to the mechanical frictions. Okay. Now volumetric efficiency given by Q upon Q plus delta Q, that is quantity discharged per second from the pump upon quantity passing per second through impeller. And mechanical efficiency is given by Q plus delta Q VW to U2 upon G into gamma upon shaft power. These are similar to the case of the turbine, just reverse of that. And overall efficiency given by gamma Q HM upon shaft power, that is manometric efficiency into volumetric efficiency into mechanical efficiency. Now minimum starting speed of the pump, this is very important topic, that is minimum starting speed, that is N value, that is starting speed can be calculated, and this is basically asked in various examinations. This is U2 square minus U1 square upon 2G. This has to be more than manometric head, and this can be determined if we put the formula for U here, that is root 2 GH. And if we put the value of U here, then this can be determined here by D2 and D1, that is pi n upon 62 whole square, D2 square minus D1 square. This is more than root 2 G HM, and N can be calculated from this equation. Now we are having NPSS, that is net positive suction head. This is head available to push liquid into the pump above vapor pressure of the water so that the cavitation cannot occur. This NPSS value can be given by P ATM minus PV upon gamma minus HS minus HFS. This is atmospheric pressure, this is vapor pressure. Gamma we all know this. This is suction head, this is the head due to the frictional losses. Now NPSS available should be more than NPSS required so that the cavitation cannot occur. Now specific speed of the centrifugal pump, the concept we all know, that is the speed of the geometrically similar pump which would deliver 1 m³ of the liquid per second against head of 1 meter, and it is given in this case by N under root Q upon HM raised to power 3/4. Okay, so this is formula very important. And in the model analysis case, for the specific speed we represent by N root Q upon HM raised to power 3/4 for model and prototype. Tangential velocity can be given by root HM upon ND for model and prototype, and power of the pump can be given by Q upon ND cube for model and prototype. This formula is also important in case of the model analysis. P upon N cube D raised to power 5. This has to be equated. And there is one concept, there is the last concept in the pump, that is the priming of the pump. Priming of the pump is the concept that is before starting a pump, its impeller and suction pipe have to be filled with water in order to remove any air or gases from the waterways of the pump. If these are present in the pump, then there will be a possibility of the cavitation, and we have to avoid the cavitation so that our pipe will not become rusted. So we provide the priming of the pump, that is the filling of the water in order to remove any air gases from the waterways of the pump. Okay, thank you very much. We will finish here with the subject hydraulic machine. So you can subscribe to my channel to stay updated. Mail me at windsofchange2020@gmail.com for any query. Thank you.